Okay, good morning everyone. Welcome back. And I guess today is your magnetic day, then is. And I will kick it off this morning by taking a somewhat deeper look into the nature and origin of spin Hamiltonians. So the rest of the day and the rest of the school, you will see the spin Hamiltonian and the use of the spin Hamiltonian a lot, also in the practicals, in the magnetochemistry and in the EPR spectroscopy. And the purpose of that lecture here is to give you an idea of a big picture overview of where that stuff comes from and what it really is. And so to get it started, I want to go back to that overview here that I gave you yesterday, and I explained to you that all spectroscopies here on the left side involve electronic excitations, and yesterday we spent a lot of time talking about what electronically excited states are, etc., etc. And today we go to the other side. And so on the other side, the spectroscopy that involves microwaves and radio waves, so many orders of magnitude less in photon energy, and see what molecular phenomena correspond to that. So and remember that everything here is happening in the ground state electronic configuration. Right? In order to drive that home, let's get you an overview of what we talked about yesterday is situations in which we go from the electronic ground state configuration into an electronically excited state by moving electrons from occupied into unoccupied or partially occupied orbitals. And that ground state, let's assume that has a total spin of S, right? And as we know, a total spin of S means you're not just having one state, right? I think that's a common mistake that people say, oh, that's a triplet state. That's okay, but a triplet state is not one state. A triplet state is 3 states, right? And a quintet state is 5 states, and a septet state is 7 states. Yeah, and in terms of optical spectroscopy, for most of it, it doesn't really matter. But it does matter as soon as you start doing magnetic spectroscopy, because once you put a magnetic field on these components, these 2s plus 1 components, and I call them magnetic sublevels, they will start to split. And they will start to split, and you can then induce transitions between these split magnetic sublevels. But please pay some attention to like the energy scales here. Let's say in optical spectroscopy we do excitations on the order of say 5,000 wave numbers to about 50,000 wave numbers or so. And these splittings here in the magnetic sublevels, they're on the order more of 1 wave number, right? And not 50,000 wave numbers. So that that is many orders of magnitude less, meaning that figure is like grossly drawn out of scale. Yeah, and that is something that you should remember. And tomorrow we will talk about the spectroscopy that combines both of those, and that is MCD spectroscopy. But I leave that for tomorrow. So let's go back and look at the very elementary properties of what an electron is, right? Of what electrons and nuclei are. So electrons and nuclei have a mass. The electron mass is me, and the nuclei have a variable mass. Of course, different isotopes have different mass, etc. And then the electron behaves as a point charge with 1 unit of elementary charge minus. And nuclei are positively charged with a nuclear charge of ZA that depends obviously on the element. But what we are talking about today is another fundamental properties that electrons and nuclei just have, and that is they act as bar magnets. Yeah, so in magnetism there is no magnetic monopole, but the first moment there is a magnetic dipole. And the magnetic dipole of an electron is just exactly as fundamental as the negative charge of the electron. It's a property that electrons just have, and a property that nuclei just have. Yeah, and so that is something we have to accept, that simultaneously the electron is a point charge and a bar magnet. Yeah, and the magnetic moment of the electron that is given by minus the free electron G value times a constant of nature, that's a Bohr magneton, and in atomic in SI units, that's 9.274 and etc. times 10 to the minus 24 joule per Tesla. And this free electron G value here, that's an anomaly. and it amounts to 2.002319, etc., and it's one of the big triumphs of quantum electrodynamics to be able to predict this 002319, etc. from first principles. So, but that is also a constant of nature. And the magnetic moment of nuclei, goes analogously. That's plus a nuclear G value that depends on the isotope, and you can look it up in tables. For example, there's a very nice table compiled by the Bruker company, and then times another constant of nature, which is the nuclear magneton. And if you compare that, so it's 9 times 10 to the minus 24 for an electron, and 5 times 10 to the minus 27 for nuclei, meaning that electrons are much stronger magnets than nuclei, right? So that that is something you should keep in mind. There is a hierarchy here, and the nuclear magnetic moment, the electronic magnetic moment is much, much stronger than the nuclear magnetic moment. That is also why NMR spectrometers and EPR spectrometers are constructed in a fairly different way. Because you need a much stronger magnetic field in the NMR in order to induce the splittings that you're probing. Yeah. Okay, and one side remark that we need here is atomic units. So in quantum chemistry, and also like practically everything that ORCA prints, is in atomic units. And atomic units is the lazy unit of the theoretical physicists and chemists, where the units disappear and everything is just one. And that is great in order to do calculations or programming, but a consequence of that is that quantum chemists got so lazy with units that every time we actually have to care about units, we are crying for help from a physicist, and it's because only physicists know how to use units. Yeah. Anyways, the important constant that we have to deal with is the fine structure constant, and here that Bohr magneton in atomic units is 1/2 the fine structure constant, and the fine structure constant is 1/2 the speed of light. And the speed of light in atomic units is 137. And 137, that's a very big number, but meaning that the fine structure constant is on the order of 10 to the minus 2 in atomic units. And most of the effects we're looking at are on the order of alpha squared, so the fine structure constant squared, and that is on the order of 10 to the minus 4 Hartrees, or to translate that into a more chemical unit, 0.01 kilocalories per mole, and that tells you that the effects we're looking here in magnetic spectroscopy are very, very small, right? Much, much, much smaller than the energy of a chemical bond or the energy change during a chemical reaction. So it's essentially emphasizing that in magnetic spectroscopy you just like very gently brush over the molecule, and you basically touch it very softly in order to to gain information. Very different from optical spectroscopy, where you hit the molecule with a sledgehammer and it changes its shape and its electron density and everything, right? So now here we're being very, very gentle. So now in order to probe anything, you need interactions, and it's we all know what happens when you put a bar magnet in a magnetic field. There's a torque on that bar magnet, and it wants to orient in that magnetic field. And that is the very same with the quantum mechanical magnet that the electron is. And it will have an interaction, the dipole moment of the magnetic dipole moment of the electron will have an interaction with the magnetic field, and that is given by minus the magnetic moment times the magnetic field vector. Yeah. Now the thing that happens that what's weird about the quantum mechanical magnets is that it cannot continuously rotate in the magnetic field, but that this interaction is quantized and there are only a few permissible orientations of the quantum mechanical magnet with respect to the external magnetic field. Yeah. And so that is essentially given. So if we have a total spin of S and then have that magnetic quantum number m sub s varies from s in integer units s minus 1 all the way down to minus s, and that gives you that 2s plus 1 magnetic sublevels or Clebsch-Gordon series, and that is the same with the nuclear spin. So these functions here, they define spin space, right? And so if you have, say, a nuclear spin and an electron spin, the combined space that is symbolized here by this tensor product symbol, that is then of dimension 2s plus 1 times 2I plus 1, right? And that is the space of magnetic sublevels that we're probing with magnetic spectroscopy. So, but these quantum mechanical magnets are not only having interactions with external magnetic fields, they also have interactions among themselves. And so that is then a dipole-dipole interaction, and if you go into any books of classical physics, the expression for a dipole-dipole interaction is the following. So that's a scalar product of the two magnetic moments. And this term here is the projection on the of the dipole moment on the vector pointing from the center of one dipole to the center of the other, and the whole thing then is proportional to the inverse cube power of the distance and between the two bar magnets, meaning that this is an interaction that dies down relatively quickly. It's relatively short range interaction. It's not super short range, right? Then, because for example, the dispersion interaction is r to the minus 6, or the exchange interaction is exponentially decaying. So you can still probe significant distances with a dipole-dipole interaction, but it's one that eventually dies out. Yeah? Okay, so that is a 10,000 kilometer high overview of what we're doing here. And the next thing we have to talk about is the phenomenology of the spin Hamiltonian. Yeah? So the plan is that to first now introduce to you the phenomenology of the spin Hamiltonian, and then go into the origin of the spin Hamiltonian parameters that we're going to introduce along the way. So here is how a magnetic experiment works. And so you start measuring a spectrum, for example, an EPR spectrum or a pulse Endor spectrum or something else. And then you obtain the primary data. And so as you see here, you have a noisy experimental trace, and you have something that follows it very closely, and that what follows it very closely is a simulation. And that simulation was obtained by fitting a bunch of parameters to the experimental traces. And so once you have that simulation, you ask yourself, great, my number is 2.41, and what does that mean? And this is where the theory comes in. So first we need to get an overview of the playing field in magnetic spectroscopy, and you can organize it in a way where you have here in the middle an external magnetic field, and that external magnetic field interacts with the electron spin, and that is the so-called Zeeman interaction. And the parameter that goes with it is the electronic G tensor, or if you want to be really nitpicky, you call it the G matrix. And I don't think it's very important to go into depth on that, but if you're interested, we can explain it. And the magnetic field, as I said, has an interaction with the nuclear spin. And in principle, you could write that, of course, in the same way as the electronic G tensor in terms of a nuclear G tensor, but that's not what we're doing in NMR spectroscopy, because we're re-expressing that in terms of so-called chemical shielding. But in principle, it's the same kind of thing. It's the Zeeman interaction of the magnetic field with the electron spin or the nuclear spin. So then we have the interaction of the electron spin with the nuclear spin, and that's so-called hyperfine interaction. And there is a hyperfine tensor A that is describing that interaction. Then there is the interaction between the nuclear spins, and that is the NMR spin-spin coupling. Then there is the interaction of the nuclear spin with itself that is happening for nuclear spins of larger than 1/2, and that is the quadrupole interaction. And there also is an analogous interaction of the electron spin with itself, and that is the so-called zero field splitting, and that is given the tensor D. Finally, if you have interacting electronic spin systems, they also interact, and that is then subject to the exchange coupling. And the exchange coupling is most of the time just a scalar, but it can be a tensor, and that is given the symbol J. So now if you look at typical ranges for these interactions, so J can range anywhere from 0 to about 1,000 wave numbers or so. The zero field splitting from maybe a tenth of a wave number to 100 wave numbers or so. The Zeeman interaction from like say 0.1 to 10 wave numbers. A hyperfine interaction about 10 to the minus 2, 0 to 10 to the minus 2. Etc., etc. And finally you have the NMR that goes, is on the order of 10 to the minus 8 wave numbers. So these are like 11 orders of magnitude in interaction energy that these interactions span, and so that's a huge playing field also for theory to connect to that. So next what we do is to briefly go through each one of these interactions and discuss what it does to the magnetic sublevels. So and the first thing, I already mentioned it, is the Zeeman interaction. And the Zeeman interaction, what it does, if you have 2s plus 1 magnetic sublevels, in the absence of the magnetic field, they're degenerate. Yeah, there is a zero field splitting, but we come to that later. So in the absence of magnetic field, these are degenerate. So if you just solve, say, the Born-Oppenheimer-Schrödinger equation, you come out with 2s plus 1 degenerate levels. And so now when you turn on the Zeeman interaction, these levels are linearly diverging. Yeah? And so they're linearly diverging according to the magnetic quantum number m. Yeah? So as you turn on the field, like these levels split apart by minus m times g times beta times the magnitude of the magnetic field. And that means you can make a transition between them by shining light of the appropriate frequency. And so the resonance condition is h nu, the energy of the photon, equals beta b times the so-called effective g value. And we're going to talk about that in way more detail down the road. But I want to mention at this point that this g value, that is the molecular quantity that we're after, right? And so that is usually written in EPR spectroscopy as a deviation from the free electron g value, right? So it's the free electron g value plus a delta g, and that delta g, that depends on molecular structure, on the geometric and electronic structure of the molecule, and that is what we are after. So if we have a resonance that is exactly coinciding with the free electron g value. So if we plot here magnetic field and then have the EPR resonance, then a delta g that is larger than 0 will shift the resonance to smaller fields, and a delta g that is smaller than 0, that is negative, will shift the resonance to higher magnetic fields. Yeah? So that is important. It's also important to notice that in EPR spectroscopy, as I already mentioned yesterday, the energy is inversely proportional to the field. Yeah? So you have the very same phenomena that at high field, like lines appear to be very, very broad, and at low field lines appear to be relatively sharp. But that is an artifact. Once you would plot the EPR spectrum on the frequency scale, something you can do experimentally, then is, and I think Alexander will go certainly into that in his EPR lecture, then these things would turn away. Just very briefly, there is that characteristic difference between the EPR world and the NMR world, and there seems to be a quantum exclusion principle. There are very, very few people do both EPR and NMR. And so that these are two pretty separate fields that have also evolved into separate terminology and quite different cultures. So in EPR spectroscopy, we express the Zeeman effect, as I said, in terms of the G shift. Yeah? And the G shift is a tensor, and it's a deviation from the free electron G value. Yeah? And in NMR, we're doing something different, and there we're expressing the resonance, the Zeeman effect, in terms of the chemical shielding tensor sigma. and that 1 minus sigma is then taking the role of the G tensor G here, and here you have basically the bare nuclear nuclear G value. That's just convention. Neither is better or worse than the other. It's just something you have to get used to when you discuss EPR versus NMR. But it's important to keep in mind that it's the same phenomenon that you're probing. It's the interaction of the magnetic dipole moment with the magnetic field. So the next interaction is then the hyperfine coupling. So let's assume we have a single nucleus with a nuclear spin that is different from 0. And then the nucleus will behave as a bar magnet too. And what will happen then is initially, say if your electron spin is 1/2 and your nuclear spin is also 1/2, then initially the magnetic field will split these levels into the m sub s minus 1/2 and the m sub s plus 1/2. And the hyperfine coupling, that is splitting these two levels again apart into the m sub I plus 1/2 and m sub I minus 1/2. And they're split by, if you do the math, 1/2 the effective hyperfine coupling constant A. All right, and so now you have resonances. In principle, now you have 1, 2, 3, 4, 5. So you have a number of different transitions, but the fact is only 2 of them are allowed, and that means you get 2 lines now instead. Where here you had 1 line, you get 2, and these 2 are split by the hyperfine coupling. Now it can happen that you have equivalent nuclei that have the same nuclear spin and the same hyperfine coupling, and then you get these funny patterns here where you have, according to Pascal's triangle, a bunch of lines that follow a certain intensity distribution, right? So for if the nuclear spin is 1/2 and you have you have 1 nucleus, it's 2 lines in proportion 1 to 1. For 2 equivalent nuclei, it's 1 to 2 to 1. For 3, it's 1 to 3 to 3 to 1, etc., and so on. And for higher nuclear spins, it goes the same way. That is a funny spectrum here. That's actually an experimental spectrum. That is a 7-line hyperfine pattern. It's pretty historic because it proved in a certain copper center that this is a copper dimer. So you get some ideas about how many equivalent nuclei you have in that system. So that is a hyperfine coupling, and analogous is the NMR spin-spin coupling. So now you have the quadrupole coupling, or the Q tensor, and that is a bit of an oddity, because for almost all of quantum chemistry, the nucleus is just a point charge. And the one place where it's not behaving as a point charge is the quadrupole coupling. And that happens in nuclei that have a spin of larger than 1/2. And in this case, there is a nuclear quadrupole moment, and that nuclear quadrupole moment, that interacts with the electronic field gradient, right? So that's a gradient of the electric field that the electron cloud is creating at the point of the nucleus. And there are 2 different shapes that this can have. It can have the cigar shape and this oblate shape here, and they have different consequences for the spectrum. Yeah? And the total charge that gives rise to that field gradient, that is the sum of the electronic and the nuclear charge. It's something that's not very hard to calculate. I know if you're doing NMR, the quadrupole interaction is something you hate. If you do Mössbauer spectroscopy, the quadrupole interaction is something you love. And if you do EPR, most of the time you don't want to deal with it. Then yeah, but it is there. It is real. It is a small interaction, but it has quite some diagnostic values. So next is the zero field splitting, and the zero field splitting tensor D, that behaves, what it does, it's splitting the magnetic sublevels even in the absence of a magnetic field. Yeah, so if you have, and it does so. Now here is the point where it's very important to differentiate between Kramer's and non-Kramer's systems. So a Kramer system is one with a half integer spin. Yeah, so 1/2, 3/2, 5/2, 7/2, etc. And so what's happening now, relativistic theory tells you that in the absence of a magnetic field, the zero field splitting cannot lift the degeneracies completely. So what will happen then is that the zero field splitting in a Kramer system splits the levels into so-called Kramer's doublets. Yeah, so pairs of two. And this is what's happening here when you have a spin 3/2 system, and the zero field splitting is splitting this into the m sub s plus minus 1/2 and the m sub s plus minus 3/2 level, and they're separated by 2d. That's a slight oversimplification that we get rid of later. But this is essentially what is happening. And then when you turn on a magnetic field, these behave like separate doublets in the case that the zero field splitting is larger than the microwave photon. Yeah? So that is happening only for S larger 1/2. And for non-Kramer systems, the situation is different, because then the Kramer's theorem doesn't hold, and the zero field splitting can split the degeneracy completely. And it does so in two ways. In one way is the axial zero field splitting, that in an S equals 1/2 system would split the electronic, the three magnetic sublevels, into the m sub s equals 0 and the m sub s plus minus 1. And then the rhombic zero field splitting, that is given the symbol E, would split further, would lift the degeneracy of the plus minus 1 sublevels. Note that the zero field splitting can be positive or negative. That means for a negative D, that whole thing turns around, and then the plus minus 1 sublevels would be lowest in energy, and the m sub s equals 0 would be highest in energy, and likewise the same can happen for a Kramer system. Yeah? Now finally here, the exchange coupling, what it does is the interaction between two separate spin systems, and that is usually described by a phenomenological Hamiltonian that's called the Heisenberg-Dirac-van Vleck Hamiltonian. And so careful, I think Dan will probably go into more detail in his lecture. There are several ways to write that. So here in Mülheim we like to write minus 2j times SA times SB, and other people write minus j times SA times SB, and the third set of people, they write plus j times SA times SB, and you have to pay attention what the convention is the authors are implying, because the sign of the exchange coupling is very important. And now if you have it with either a plus or a minus sign already in the Hamiltonian, that tells you there are different conventions of what is called ferromagnetic coupling or antiferromagnetic coupling. So for antiferromagnetic coupling, then you get the interaction. I think this is completely wrong here for some reason. But you have the minimal total spin lowest. And then what the Heisenberg Hamiltonian creates is a so-called spin ladder of total spin states that differ by multiples of the exchange coupling constant J. Sorry, I will revise that slide here. Yeah, and so antiferromagnetic coupling is if the lowest possible total spin is lowest in energy. Ferromagnetic coupling is when the highest possible spin of the two subsystems is lowest in energy. One side remark, because we won't have time to get into very deep detail about it, is there is no such thing as an exchange interaction in nature. Yeah, then so somebody already asked me about it. That is a misconception that you very often find in books. The exchange interaction is not a genuine physical interaction. So there is nothing in nature that carries the label exchange interaction. What it is, it comes about as part of the electrostatic interaction. It's part of the electron-electron interaction, right? So that interaction that is just like 1 divided by the distance between the two electrons. And so the fact that electrons repel each other. And that combined with the fact that electrons are fermions, right? The fermionic nature of electrons, it demands that the many-particle wave function is antisymmetric with respect to interchange of two electronic coordinates. That is something that is not intuitive. It has no counterpart in classical physics or anything that you can experience by yourself, but it's something that the pioneers of quantum mechanics have worked out. Yeah? And now the consequence of that anti-symmetry is that in the expressions for the energy of a many electron system, there appear these terms that are exchange terms, yeah, and they're not intuitively graspable, but they're not a separate interaction. They're just simply the interplay of the Pauli principle, the fermionic nature of the system with the electron-electron repulsion. So in a parallel universe where we could turn off the electron-electron repulsion, the exchange terms would immediately go away. Yeah. So please take that into account when you read about the exchange interaction. That is that is not a genuine separate interaction. Then is, yeah. Okay. So now our task is the following, and I have now phenomenologically introduced all of these parameters: the G-tensor, the chemical shielding, the hyperfine tensor, the zero-field splitting tensor, the quadrupole tensor. And now we have to worry about what does it mean? Like, where does it come from and how does it connect to the actual geometric and electronic structure of the system? And so here is the overview of what that means. So you have the primary data, which is the magnetic spectrum. And that has some connection to the molecular geometric and electronic structure, obviously, and because that is calculatable by quantum mechanics. And so what you can do in principle is to write down the entire Hamiltonian for the universe, so to say, right? And that requires introducing relativity, and it requires introducing external magnetic fields into the Hamiltonian, and then you have a horrifically complicated equation to solve, but you could do that, and then you would be able to to calculate the spectrum. And if that is what people had to do, I don't think any EPR spectrum would have ever gotten analyzed. Then is right, because we need something way simpler than that. Yeah, and so that thing that is way simpler than that is the spin Hamiltonian operator, right? And so the spin Hamiltonian is a Hamiltonian that only contains spin variables and magnetic field variables, right? So this one here contains the coordinates and spins of n electrons. Terribly complicated. This does not know anything about electrons, it only knows about spins. Yeah? So that's a much smaller dimensional space, and it's acting on these spin functions. So for example, if we have one nuclear spin and one electron spin, it's at 2s plus 1 times 2i plus 1 dimensional subspace. So it's a tiny fraction of the Hilbert space of the entire system. And so the great thing about that, now that leads to Schrödinger equations that can be very easily solved, either by hand or with a computer. And the price that we have to pay for that simplicity is that we have to introduce these parameters, the G matrix, the zero-field splitting tensor, hyperfine tensor, etc. And so we get values, numerical values for those by fitting them in comparison with the experimental data. Yeah? So that is then the interplay of fit and simulation that gives you numerical values for these spin Hamiltonian parameters. And now the job of theory is now to make the connection between the first principle physics here and the effective physics here. Yeah? So the spin Hamiltonian is what we call an effective Hamiltonian. Yeah? And now the job of the theoretician is to make unambiguously clear what the connection between those first principles and this effective physics is here. And that's complicated. If we go into deep detail, we could talk about it for the entire week. So I will give you only like a brief overview of what is involved in getting there. Yeah? And the value of the spin Hamiltonian and the interplay of the spin Hamiltonian and the quantum chemistry, I think, can hardly be overemphasized, because spectra can get very complicated. So once you have many nuclear spins and a couple of electron spins, and you have a high resolution technique like pulsed Endor or so, these simulations become very, very tedious. And so I've been involved in many Endor studies in my life. And every single one of them ended in a way where people weren't able to really fully simulate their experimental data without the help of quantum chemistry. But once the quantum chemistry came in, the fitting got much easier. So that's one of my friend and collaborators, Daniela Goldfarb, and like she once sent me an email and saying like, please see attached, and it shows that the experimental high scores and the simulated one and the one is that we fitted and the one with the parameters that we've calculated, and say agreement is rather good, even better than our simulated ones. So the value here that the quantum chemistry brings to the table is that it gives you really great starting values for these simulations, right? And so because you normally have way more to fit than the experimental data will allow you to extract unambiguously, and you can really, really aid this fitting by recourse to quantum chemistry. Yeah. So, and it also greatly helps in interpreting the information content of these spectra. For example, characterizing intermediates, and then the other thing that I've emphasized that once you have these, the connection between the quantum chemistry and the electronic structure, you can use it as a falsification process for your data, and it's also fun. Now, if you really want to read about that yourself, because that lecture will go much faster than probably you'll be able to digest it. I recommend a small book, so that's a Dover publication book, so you can buy that for dirt cheap on the internet, and that's written by a guy called Roy McVinney, and it's like maybe only 90 pages or so, but Roy McVinney was one of the eminent theoreticians of the last 100 years, and that book came out of a series of lectures he gave to a general chemistry audience, and it's really easy to read, and everything that's in there is correct. Now, unfortunately, to the EPR people among you, then is every EPR textbook contains a section on theory, and every single section of every single EPR textbook is completely wrong. So these people are wonderful spectroscopists and great scientists, but not one of them is a quantum chemist, and all of the quantum chemistry that is in the EPR textbooks is extremely flawed, right? And so you get really flooded with misinformation and mistakes in there, and so please don't rely on that. Read a proper textbook, and McVinney is one that is a proper textbook. Okay, so just bird's eye overview. I've already shown you this picture, so this is essentially that 99.9% of all of the physics that's happening in chemistry is coming from the Born-Oppenheimer Hamiltonian, and in the Born-Oppenheimer Hamiltonian you have a bunch of positively charged nuclei that are assumed to be at rest, and then you have the electron cloud that is swirling around these nuclei, and the one interaction you take into account is just the Coulomb interaction, meaning the repulsion between these two electrons. You have the kinetic energy of the electrons, but not the kinetic energy of the nuclei because they're stationary. And that, together with the laws of quantum mechanics, that gives you your many particle wave function and the electronic states we talked about so much yesterday. So in order to do EPR, you need much more than that. Yeah, and it's one place where you need more than that. And the more that you need here, that is the theory of relativity. And I definitely do not want to go into any depth of that, but just briefly where it's coming from. So there is the equivalent of the Schrödinger equation for a single electron, and in relativity that is the Dirac equation for a single relativistic electron. It's mind-bogglingly bizarre, then it's because it creates that parallel universe of electrons and positrons and all that, but every single prediction that the Dirac equation made is correct. And now the generalization to many electrons, that is the so-called Dirac-Coulomb-Bright equation. That's already a very, very complicated equation. But if you take the non-relativistic limit of this, then you recover the Born-Oppenheimer Hamiltonian. Yeah? So that is the logical flow. But in the process, you can separate out a relatively large number of additional small terms in the Hamiltonian. And these are so-called scalar relativistic correction. So these are spin-free terms arising from the relativity. They do all kinds of things, including deeply stabilizing S and P orbitals and destabilizing D and F orbitals. So gold has the color of gold because of relativity. And Mercury is a liquid because of relativity. These are the two examples that you that you always get quoted. And then, and that's important, the second term here, that is the spin-orbit coupling that is coming out of the relativistic treatment. And the third thing is the magnetic field interactions. And so now what you can do is you take as a starting point the Born-Oppenheimer Hamiltonian, and then you add in these small relativistic and external field corrections via perturbation theory in one way or another. And that is then how you can express all of these magnetic interactions. So on the next slide, I want to scare you a little bit, and so this is not meant to be, this is intentionally anti-pedagogical. So these are the explicit expressions for all of these relativistic terms and corrections, and obviously we're not going to study all of them here, but so they are closed form expressions. Unfortunately, it turns out that there is multiple ways in which you can do the decoupling of the relativistic degrees of freedom and the non-relativistic degrees of freedom, and this is based on the oldest of them, that is so-called Breit-Pauli expansion, and the Breit-Pauli expansion unfortunately diverges for heavy elements, and so that is still a research field in quantum chemistry. It's a relativistic quantum chemistry, and new expressions for that emerge all the time. I note one thing in passing that I've been fighting without any success for the last 30 years, and that is in many textbooks you find the spin-orbit coupling written as lambda times a capital L times capital S, where capital L is the angular momentum operator and capital S is the total spin operator. This is really a mistake. That leads you to all kinds of wrong conclusions, and unfortunately the original papers where the spin Hamiltonian was proposed were using this form of the spin-orbit coupling, and the result was that in the pioneering Abraham and Price spin Hamiltonian papers, the equations are completely wrong, just because they were using a spin-orbit coupling operator that was completely wrong. Yeah. So one of the very, very wrong predictions that comes out of that is that the G tensor and the D tensor are proportional to each other. This is idiotic. Then it's just simply wrong, but it's stated in all textbooks. And no matter how many times you argue against it and prove that that's wrong, it will still forever be in the textbooks. But please don't do this. It leads you to wrong conclusions. Okay. Now, let's assume then that we have the following situation, that we are in the fortunate situation that we have solved the Born-Oppenheimer equation exactly, which we can't, right? We can't even do that for the helium atom, but let's be good theoreticians and do something completely unrealistic. And let's assume that we have solved then the Born-Oppenheimer equation exactly, and we know all of these excited states. So let this be our electronic ground state. So that's in this case a triplet state with its 3 triplet components, and then we have all of the excited states, like moved our electrons around it, etc., and we have solved it. And now we divide that total space of an infinite number of electronic states into 2 sets of states. And the first space is a model space. That is just like the magnetic sublevels of the electronic ground state, because that is exactly the levels we probe in the EPR experiment, and that is the number of levels that is equivalent to those in the spin Hamiltonian. Yeah? And everything else we call the outer space. Yeah? And so basically what we now have to figure out is how the outer space is coupling via all of these relativistic operators with the sublevels of the magnetic ground state. And if I would do that explicitly, it would take us all day. So there is a long road. So we are here, and so if you travel along your mathematical route, you eventually end up there, and that will give you explicit expressions for the spin Hamiltonian parameters in terms of the magnetic ground state levels and the set of excited states. So in all of these equations for the spin Hamiltonian parameters, you always have two types of terms. And the first order terms, that are those for which you only need the magnetic sublevels of the ground state, and I write them here as ASS. Yeah? So A is our model space, that is the electronic ground state, that is the primary magnetic sublevels we want to probe, and everything that is the first order terms is just arising from the relativistic operators and those magnetic sublevels of the ground state. And for example, here for the G tensor, that is then the expression for the first order terms for the G tensor. It starts with the free electron G value. So that is the first term that you get out of the relativistic treatment, is the free electron G value. And then you get the first relativistic correction. That is a correction for the reduced mass. And the second one, that is the so-called diamagnetic term in the EPR G tensor, that's equivalent to the diamagnetic term in the NMR, and that's a relatively complicated operator that I don't want to discuss in any level of detail, but it's in principle just an expectation value over the electronic ground state. Yeah. So now to second order, then you have the coupling of the electronic ground state levels with the excited states, the entire infinite number of outer space states B. Yeah? And so characteristically, now there always is the inverse of an excitation energy. Yeah? So the closer the outer space state is to the magnetic ground state, the larger its contribution will be. And then you characteristically also have a product of two perturbing operators. And those two perturbing operators are chosen in a way that it gives you the correct terms in the spin Hamiltonian. So in terms of the G tensor, this one here, that is the orbital Zeeman term. Right? And so that came from the operator that is coupling the angular momentum of the electrons to the external magnetic field. Yeah? So the physics here is that as the electrons are in motion, and you can think about them as being on a circular path, that charge in motion creates a magnetic dipole moment. Yeah? So for example, it's the same as if you have like a piece of wire and you send a current through it and then put it in a magnetic field, it will start to orient because that current in the wire will create a magnetic dipole moment. And that is the same, that is essentially what the orbital angular momentum does, right? And that is a term that is then proportional to L times B, right? And the other term here, that is a spin-orbit coupling, and that is proportional to the electron spin S. Yeah? And so what you have then here, the G tensor is like B times G times S, right? So you have chosen your two perturbing operators so that one contains B and one contains an S, right? And so in principle of that like laundry list of like relativistic terms, anything, you can pick any pair that where one has a B and one has an S, and that will contribute to the G tensor. So that is in principle how these things are done. Yeah. Now for the G tensor, it turns out that only excited states contribute where the total spin of the outer space state is the same as the electronic ground state. That is important, right? So to that leading order in perturbation theory, so if you have a doublet state, only other doublet states will contribute. So excited quartet states or sextet states will not contribute to the G tensor, only those with the excited states. Yeah. You can also see from this one, so essentially that is the expression for the G tensor for element KL, where K and L are X, Y, or Z. And that is then the Zeeman term times the spin orbit, and this is like the way round. And if you look at it, you will see that this is not symmetric. Yeah, so the G, that's why G itself is not a tensor. Yeah, G itself is a matrix, and that matrix is asymmetric. And it turns out that what you probe in the experiment is not G itself, but it's the square root of G squared. So GT times G, that is a tensor, that is symmetric, and what you're probing is the square root of that. Yeah, there are super sophisticated experiments that can actually determine the absolute sign of G, but normally you cannot. Yeah, that's why it's a bit nitpicky to make the distinction between the G matrix and the G tensor. Yeah, so it's used interchangeably in the literature, but if you want to be pedantic, then you call it the G matrix and not the G tensor. Yeah, okay. So that is then how, in principle, all of these spin Hamiltonian parameters emerge, right? So you start from the solutions, the non-relativistic solutions of the Born-Oppenheimer Hamiltonian, and the Born-Oppenheimer Hamiltonian does not contain spin or relativity or external fields. And then you introduce them by perturbation theory. You do that partitioning technique between the model space functions of the electronic ground state and the excited state functions. Then you dump in all of these relativistic terms, and then with a bit of algebra you can derive all of these equations, right? So now that has some slight practical problems, and the first practical problem is we can't solve the Born-Oppenheimer Schrödinger equation, right? And we cannot calculate an infinite number of excited states. Yeah. And so you need something more practical. And so what you do most of the time when you run an ORCA calculation is not that, but it's something different. And that something different is so-called linear response theory. And that pertains to basically any electronic structure method. So for Hartree-Fock theory, or for Cassis theory, for density functional theory, or coupled cluster theory, or MP2 theory, that is a very universal way of approaching molecular properties. And so each one of these methods gives you an energy. Yeah? And now you have an approximate energy, and now you start putting in these perturbing terms, right? Like external magnetic fields, electric fields, relativistic terms, etc. And the energy will change, right? So if you plot now the energy as a function of that perturbation parameter, say lambda, something funny will happen, right? And but there's one thing you can always rely on, that as long as the perturbation is small, so lambda is small, the rate of change of the energy as a function of lambda will be linear. Yeah? And the slope of this divergence here, so the first term in the Taylor expansion, that is called the linear response of the system to the perturbation. Yeah? And so that's a very nice way of doing it. Yeah? So basically you only have to then take derivatives of your approximate energy. And like taking derivatives is something that quantum chemists are good at. And that is something that's way more approachable than calculating an infinite number of excited states. And it turns out that almost all molecular properties can be expressed as a mixed second derivative of the total energy with respect to two perturbations. And the type of terms that you have in there are twofold. The first one contains the electron or the spin density of the electronic ground state, that is at p plus minus here, and then the second derivative of the Hamiltonian with respect to two perturbations. So in terms of like what I've talked about before, say all of these relativistic corrections, let's think about the G tensor. That would be a relativistic term that contains B and S by itself. Yeah, for example, the spin Zeeman term would be of that category, right? And then the second derivative of it, that would be the term that ends up in the spin Hamiltonian. And the other one is then the first derivative of the electron or spin density. So plus would be the electron density and minus the spin density here with respect to one perturbation times the first derivative of the Hamiltonian with respect to the other perturbation. There, funnily enough, is an interchange theorem that tells you it doesn't matter whether you take the derivative with respect to kappa or the derivative with respect to tau. That gives you the same results, and you can choose the one that's more convenient. For example, in NMR, that's important when you want to calculate the chemical shielding tensor for like 1,000 nuclei. You will only need to solve the so-called response equation set, what's take the time, with respect to 3 magnetic field components. And then you can calculate basically the chemical shielding tensors for 1,000 nuclei. If you would do it the way around, you would have to solve like 1,000 response equations for each nucleus separately before you then contract it with the magnetic field integrals, and that's a pain in the neck, and that's why you have the freedom to choose the order of in which the perturbations are done. And of course, you as a user of quantum chemistry program, you don't need to worry about it because we have done that for you and have implemented in a way that we think is optimal. Although all of this is always in flux. So for example, the next ORCA will have a different way of calculating the spin-orbit coupling contribution to the hyperfine that's way more efficient than the one we've used the last 20 years. And so if you do that, then that's another intentionally anti-pedagogical slide. So you can express all of the spin Hamiltonian parameters in terms of these electron densities, spin densities, and then and these response densities. And the response densities are the derivatives of these densities with respect to external perturbations, and then those property integrals. I know that's a lot to swallow, and like I'm not expecting that anyone is internalizing these equations, but I hope that I've motivated like the general outline of how you arrive there, and that it's a completely different way of thinking than what I've shown you before. Because now this stuff here pertains to every approximate method, right? So as long as you are able to calculate an electron and a spin density and its derivatives, it looks the exact same for whether it's coupled cluster theory or it's full CI or it's density functional theory or it's XTB, or it's all the same. And when we rewrote ORCA from ORCA 5 to ORCA 6, we took advantage of that by making sure that every single approximate method, as soon as it's able to deliver an electron or spin density, all of these properties can be immediately calculated, right? And so that's what the ORCA prop program does, right? So you will see that if you compare the executables from ORCA 5 to ORCA 6, you will see that like we've kicked out some legacy modules and put new ones in, and now there is a module that's called ORCA prop in that is calculating all of these strange property integrals. And there is another program that's called RESP that is calculating all of these response densities. And so basically now it's all using one and the same set of codes, and that has eliminated millions of lines of code literally. Then is where we did like G-tensor calculation for coupled cluster and G-tensor calculation for MP2 and G-tensor calculation for Hartree-Fock and G-tensor calculation for DF2. That's no longer happening. The only thing we basically calculate is these densities and response densities. We contract them with these property integrals, and everything's the same. That means as soon as a new method is available, you immediately have all of the properties available, and that is coming out of this way of thinking. Okay, so here is then the takeaway from the horror slide. Yeah, so in order to calculate spin Hamiltonian parameters, you only need the electron and or spin densities and the derivatives of the electron or spin densities, and that's the response densities, and then these property integrals. And that single equation then is covering not only all EPR parameters, but for example also all electric properties like a polarizability and a hyperpolarizability, You can express the VCD intensity and like the Raman polarizability. It's all of this is expressible the same way. Now there is then a situation, and like those of you who work in molecular magnetism, and I know there are a couple of you who do that, they face a different situation. And that different situation is met when the linear response theory breaks down, or that perturbation theory I've shown you before also breaks down. And then we approach magnetic properties in an entirely different way, and that is called quasi-degenerate perturbation theory. And that is used in conjunction with all of the multi-reference methods that we have in ORCA. And I briefly explain that to you now. So both the linear response theory and that sum over states perturbation theory that I talked about rely on the fact that there is a clean separation of the ground state magnetic sublevels and those of the excited electronic states. And not all molecules are constructed that way. I mean, for example, there are molecules, especially transition metal complexes, that exist in electronically degenerate states. And there you don't have such a separation. Or it's a nearly degenerate electronic state, then you also don't have that separation. And in this case, what you have to do is to treat all states on an equal footing. And what's happening then, the way that is being done, is to actually then really try to calculate approximate eigenfunctions of the Born-Oppenheimer Hamiltonian. But then instead of using perturbation theory to introduce these small terms, you pack everything together, like the Born-Oppenheimer, the spin-orbit coupling, that is the electron-electron spin-spin coupling, and the Zeeman term, etc. And you pack all that in one big matrix, and that is called the quasi-degenerate perturbation theory matrix, or the master matrix, and then you brute force diagonalize it. And then you can indeed calculate magnetic properties directly from these relativistic many-particle eigenfunctions rather than taking the detour of the spin Hamiltonian. As long as you don't have to do that, I recommend to not do it, because the linear response is way more elegant and way more efficient. But in cases where you have electronic degeneracy or near degeneracy, that's your only choice in order to arrive at a reasonable result. Yeah? So you may have sometimes like wondered where you have been using DFT to calculate a G-tensor, and for example you applied it to I don't know, a chromium-3 complex, and it was not so bad. And then you went to a high-spin iron-2, and hell broke loose, and everything went to pieces, or the low-spin iron-3. You say, what's happening here? And what's happening there is that these, by means of ligand field theory, these have electronically degenerate ground states, and there's a bit of splitting from the Anteller effect, etc. But what's just happening is that the linear response theory breaks down, and you get a completely nonsensical result from it. And that's not because the program has a bug or anything, that is because that's real physics. And in that case, you will have to go to a multi-reference method and treat it that way. It's also for those of you who work with lanthanides or actinides, the way to calculate the magnetic properties is definitely this way, and not via the linear response theory. Yeah? And the reason for that is just simply that in these very heavy F elements, the spin-orbit coupling effects are so large that they will invalidate the linear response theory. Yeah? Okay, so the strength of that approach is that it's, if you want, so infinite order treatment in perturbation theory. Yeah? So you're not making any assumption of the relative strengths of the perturbations or the separations of the states. The mapping onto a spin Hamiltonian here is difficult, but it stays valid even when the spin Hamiltonian breaks down. Yeah? And the weakness of it is, of course, there is a truncation error, because the results will depend on how many states you calculate, right? So you say you calculate, you decide, I calculate 10 states. And the next person decides to calculate 12 states and gets a different result, and the next person decides to calculate 25 states and still gets a different result. So there is a truncation error that you have to watch. Now, if you are if you are guided by ligand field theory, you will know how many states you need in a given multiplicity in order to saturate that space. Yeah? Then you still have a truncation error, but a truncation error that is very systematic, and you will catch the very large contributions. Let me give you an example. So where the spin Hamiltonian is not valid, so a real life example. And it's important that you keep an eye open for that, right? Because you saw it, especially in the early days of molecular magnetism. People had systems with orbitally degenerate ground states, and they were mercilessly fitting a spin Hamiltonian to it, and then you create numbers that literally make absolutely no sense. Yeah, and and that's why it's important to understand where this stuff comes from, and as long as it's valid. So the spin Hamiltonian is a wonderful invention, beautiful. It's a real, true intellectual accomplishment of the community. But every once in a while, it just doesn't apply. And then it's your job as a scientist to figure out when that's the case. Yeah? So, and that is the case when it's the following. So the normal situation here is that you have that ground state multiplet, 2s plus 1 magnetic sublevels, and then you have an excited state multiplied here, 2s prime plus 1 components, and their separation is, say, like on the order of 10,000 wave numbers or more, and then you have a spin orbit coupling that is, like, say, on the order of 100 wave numbers or 2 or 300 wave numbers, but definitely still much smaller than that separation here. What will happen then is then this perturbation or any of the others I've talked about is creating like splittings on the order of, say, roundabout 1 wave numbers. Yeah? And that would then be probed by an EPR experiment. Everything is honky-dory, is nice and beautiful, and you can express it in terms of spin Hamiltonian, everything's nice. Now, the other situation arises now when that separation is no longer large, right? Because what will then happen is that these magnetic sublevels will somehow mingle and merge with the other, with the ground state magnetic sublevels, and then hell breaks loose. Yeah, and then you can get all kinds of things like standard spin Hamiltonian doesn't apply anymore, perturbation theory doesn't apply anymore, linear response theory doesn't apply anymore. That means all of DFT is going out of the window, not applying anymore. And in this case, quasi-degenerate perturbation theory is inevitable. So now you have the privilege that one of the great pioneers of this is sitting right here in the front row, and he can tell you everything about it. That is Mikhail Atanasov. And a few years we have studied the following series of linear iron 2 compounds. So this is a series of compounds like Jeff Long, our friend from Berkeley, has synthesized many of these and magnetically characterized them. And they have then different ligating ligands, so either nitrogens or carbons or oxygens, and some of them are also slightly bent. Yeah? And now what's happening now, when you look at the non-relativistic state, so this is high spin iron 2, so you have a quintet state, and you have 5 ligand field excited states. Yeah? And the lowest state is a quintet E state. So you see that the lowest non-relativistic roots that you would get out of, say, CAS-SCF calculation, they're very, very close to degenerate. And like based on that slight asymmetry in the in the ligand sphere, you have in different systems more or less splitting of the degeneracy, except this system 6 here that is slightly bent. All right. Yeah, and so that is the molecular orbital scheme here. And now what's happening, what you see is exactly that, because in all of these systems, those magnetic sublevels run into each other and you get crazy magnetism. And you see that nicely when you now turn on the spin-orbit coupling and diagonalize the QDPT matrix as I have explained it to you, now you have a dense manifold of 10 electronic states. These are 10 relativistic states, and they come from the two spatial components of the quintet E state, right? So the first quintet E state has 5 components, and the second component of the quintet E has also 5 magnetic sublevels. So you have a total of 10 magnetic sublevels that after you turn on the spin-orbit coupling look like that. And so now if you have a S equals 2 spin Hamiltonian, you have just 5 levels in that spin Hamiltonian. It's a 5-dimensional Hamiltonian, and now you try to fit these 10 levels where there is no discernible gap here anywhere, right? So there isn't, it's not really grouping into a set of 5 and another set of 5, right? These are just 10 dense levels. And when you try to fit then a 5-dimensional spin Hamiltonian to it, it's completely unphysical, and the results that you're getting are completely nonsensical, and none of these spin Hamiltonian parameters you get from this fit make any sense. That's different, obviously, here in that system 6 that is bent. There is a clean separation, right? There is a clean separation between 5 and another 5. So there is a discernible gap here, and then the spin Hamiltonian makes sense. But for all of these first 5, it makes absolutely no sense to fit a spin Hamiltonian to it, right? And that is the thing I want you to understand, and then use QDPT instead. And an even crazier one I think Michael studied and then later made a prediction for an even crazier one that was later then synthesized, is the iron 1 analog. And that has even crazier magnetism because it has an even weaker ligand field. And so what you see here that you can actually calculate then the magnetic susceptibility or any of the other magnetic properties and spectra directly from the QDPT, and it's often an excellent agreement with the experiment. And that is the right answer for the right reason. And there is no recourse to any spin Hamiltonian anywhere. So if you ask me, so what's the zero field splitting of that molecule? I say, I don't know, because the concept of the zero field splitting makes no sense, right? But you have just this 10-dimensional space of relativistic many particle states, and that is what you will have to treat in order to get the right numbers for the right results for the right reason. Yeah. Okay. We have still a few minutes, and in these few minutes, what I want to do is to walk you a little bit through how to calculate spin Hamiltonian parameters in ORCA, and I think like later in the practical, you will do a lot more than that. So that's a G-tensor, and so that is a very simple way to calculate it. So there is an input block EPR NMR, and all you have to do is to set G-tensor to true. And there is not much more that you can mess with, but one thing I wanted to point out that is unfortunately not on the slide, but the G-tensor is not gauge invariant. And what do I mean by that is that the results depend on where the origin is. Yeah, so whether I like say this is the origin of the universe, so coordinate 0, 0, 0, whether I put the molecule here or put the molecule there makes a difference. And that comes from the angular momentum operator, because any angular momentum is always only measured with respect to relative to a reference point, right? And so it matters where you put that reference point. And if you put that reference point 500,000 light years away from the center of mass of the molecule, you get a very different result as if you put that reference point into the center of mass of the molecule. Now, that's obviously unphysical, because that's an artifact of how we calculate things. And there is a way that quantum chemistry has found to get rid of that problem, and that is the so-called gauge including atomic orbitals. That is something for, I mean, as I used to say, that's a subject for people who have murdered their mother and father. It's a very unpleasant technicality to deal with. But you get that if you put, there is a variable here in that input block that's called ORI for origin. And if you set that to GIAO, then the program will use these gauge including atomic orbitals, and you will get a gauge invariant result. So in this case, you can put the molecule anywhere, and you will get a fine result. The G-tensor now is known to be only weakly gauge dependent, and so most of the time you get away by choosing a reasonable origin, and a reasonable origin is then the center of spin density or the center of electron density or the center of mass. That will not vary very much. My personal recommendation would be, if you don't use GIOs, then use the center of the spin density. That makes the most sense, and the manual will tell you. I think it's then called ORI equals center of spin dense or something. Then is, yeah, and the manual will tell you how to do that. If you do an NMR calculation, you absolutely have to use these GIOs, or the results will be completely unusable. Then is right, and that obviously is then also the default that the program will default to when you calculate chemical shifts. Now. When you do the QDPT weight of calculating a G-tensor, then you have to do a bit more. For example, here in the MRCI block, so MRCI is one of the multi-reference methods that we have, but it's completely analogous than if you use CAS-SCF or CAS-SCF and FPD2 or ROSIS or any of the other multi-reference modules. You have to tell the program what terms to include in the QDPT, and so do SOC, that is including the spin-orbit coupling, do SS, that is including the electron spin-spin coupling, that is a contribution to the zero field splitting, and then you have to tell it how many doublets you want to have the G-tensor for, right? So n dub G-tensor, that is the number of Kramer's doublets that you want to calculate the G-tensor for. And then you have to tell the program, of course, like what multiplicities you want to include and how many roots you want to include in each multiplicity for the QDPT treatment. And provided you have made good choices then here, and I very, very, very strongly recommend to not do that in blind flight, but use ligand field theory as your guide, because it will give you a valid answer, like a valid guideline of like what multiplicities and how many roots you have to use. And in case of doubt, if we have also written quite a number of reviews where we have tables where you can look up the correct number of roots and multiplicities and etc. for each of the DN configuration. And then the program will print something like this, the raw matrix, and that is then happens in this case to be already pretty much diagonal. Then the diagonal is the square root of the eigenvalues of the G squared matrix. That is then the actual G values, and there are 3 of them because G squared is a tensor. And that here is then the eigenvector belonging to that eigenvalue, and so that is essentially the direction that applies to this G value. So in this case, this is pointing pretty much along the negative x direction, and that sign doesn't mean anything then, is right, because you can multiply any of these eigenvectors by -1 and it's still an eigenvector. Yeah? So the one thing that the program will ensure is that these 3 vectors, they're orthogonal to each other, span a right-handed coordinate system. Yeah? And so what is that? So if you would take a crystal of that molecule and would orient the magnetic field along the direction given by that eigenvector, you would measure this G value. And if you would put it then along Y, you would get that G value. If you put it along Z, you would get that G value. Yeah, so that is the reason. So you sometimes what you do, there is also a file produced by ORCA that's called GORI.xyz that contains some fake atoms that are arranged in a way that you can visualize that how that coordinate system sits in the molecular frame. That is particularly important for the zero field splitting tensor, where you want to know like where in the molecule is the easy axis of magnetization, for example. And you visualize it by visualizing the eigenframe of the magnetic tensor. Now, of course, if you have, like, say, a zero field splitting tensor and a G-tensor simultaneously, they're not diagonalizing necessarily in the same coordinate system, right? And so that is what we call non-collinear tensors. As a person doing EPR fitting, you will hate that. Then it's because normally without any quantum chemistry, you have no good handle on, like, how these how these axis systems are oriented in the molecule. And especially when you, like, simulate Endor, when you have, like, a ton of hyperfine tensors and you don't really know the eigenframe relative to the G-tensor, this is where quantum chemistry can come in. Now, the most EPR simulation programs express this in terms of, like, 3 Euler angles, and that is also a very nasty subject. But so ORCA has a little module that prints these Euler angles for you, and don't take them as carved in stone, but these are great Euler angle values to start your simulations from, and then, like, use those, allow them to vary by, like, 10 or 15 degrees, and you're good. Most of the time you're good. You're way better off than trying to fit 36 Euler angles and hyperfine values to an Endor spectrum that almost guarantee to end you in a local minimum. Yeah. Just briefly, like, how good are these G-tensor predictions? And this thing is for radicals, it's actually usually not so bad with DFT. There are some areas where there are significant outliers, and that usually has to do with situations where DFT gets a spin distribution wrong. And so DFT, you have to understand, has a tendency to over-delocalize the spin. And that's a result, it's a well-known artifact that's coming from the fact that in DFT, electrons are a bit schizophrenic and they interact with themselves. And that self-interaction error in effect leads the spin to delocalize too far. Now, the more Hartree-Fock exchange you put in your density functional, the less you will have that, but the more artifacts you will have also from spin contamination. That is roughly a bird's eye view of how you have that. And those radicals where the predictions are very wrong, that's usually also those radicals where just the spin distribution is very wrong. And now DFT and transition metal G-tensors, that's not a love story. That is usually not very good. So you easily have errors of a factor of 2. And that's a 25-year-old slide from the first time I ever did that. And in the last 25 years, it has not gotten any better. So that is still the state of affairs, that these transition metal G-tensor predictions from DFT are not very good. And they tend to be better from QDPT unless you have quite a lot of covalency in the metal ligand bonds, and then the QDPT is bad and the DFT is bad, and you don't have any method that is producing proper numbers. Coupled cluster is, but coupled cluster is not yet applicable to large, at least G-tensor calculations with coupled cluster are not yet applicable to large molecules. We're working on it, and I hope that within the next 1 or 2 years that'll be available, and that'll be the only way out of that misery of inaccurate G-tensor predictions for transition metal complexes. And so, but you see, there still is a lot of research to be done. But if you look at statistics like that, so there is really no reason to take a DFT calculation all too serious when you calculate G-tensors of transition metal complexes. I think I probably want to stop here. I mean, there is material for another 2 or 3 hours in the lecture notes, but I think it's probably more productive if we discuss a little, and then if you want to look in the lecture notes and have additional questions, or you have questions about the specific systems that you're studying, then please feel free to ask them anytime. Okay, so far for now. I hope that I made it took a bit of mystery out of what the spin Hamiltonian is and where it comes from, and the rest of the day you will get a lot of spin Hamiltonians and spin Hamiltonian parameters, and see them in action and how to use them. Yeah, so thank you very much.